Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. It's great to be back with all of you today. I'm excited to delve into some really fascinating stuff. You know, the usual. Trying to figure out how our brains work and if we can build something that, well, does the same thing.
Yeah, exactly. Always an adventure, isn't it? I saw this interesting paper last week, actually, on scaling laws and large language models. It's pretty compelling evidence that we're really on the right track with the deep learning approach. I think we're starting to see some real emergent intelligence there, you know?
Emergent intelligence, I don't know. I still have serious doubts about that. It feels more like incredibly sophisticated pattern matching to me. I mean, we're throwing massive amounts of data at these things, and sure, they can generate convincing text or images, but is that really understanding?
I'm with you on that, to an extent. It feels like we're trying to brute force our way to intelligence. The way these models are trained is, well, it's just massive. I mean, are we really getting at the core of what cognition is? My gut feeling is that we're missing some fundamental principles around how information is represented and processed, especially in a spatiotemporal context, you know?
Right. So it's interesting because you're both pointing out, in different ways, limitations. I'm always thinking about bridging these gaps by, looking closer at the neuroscience. I mean, our brains, they're not just pattern matchers. They're constantly constructing and updating internal models of the world in a really dynamic way. We need to incorporate that into AI, right? Like, how do we get these systems to have that kind of embodied understanding, a more holistic and integrated approach, where perception isn't just some static input, but something that informs action, and the loop continues?
Yeah, that's fair. But the recent advances in deep learning, especially with transformers, have been so fast. I mean, look at GPT-4 or these new multimodal models. It's not just about text anymore. They're starting to integrate visual and audio information. And the scale of these models is incredible. We're seeing these models becoming more and more capable just from scaling up, without needing much change in the architecture. It's almost like the intelligence is baked into the data, and we just need to unlock it by training bigger and bigger models. It might be simpler than we thought. The emergent properties might just be a result of this immense complexity.
But that's my point. It's about scale, not actual understanding. We're essentially using statistics on these massive data sets. And then when we try to go beyond that, we hit a wall. It's not like these systems are learning underlying principles of the world. Take causal reasoning, for example. Deep learning models struggle with that unless you explicitly encode causal relationships in the training data, which sort of misses the point. It's like they're great at saying A is often followed by B, but they can't understand why. You need neuro-symbolic approaches to get to something meaningful, combining the raw data with symbolic representations and rules.
Exactly. And it's not just causal reasoning, it's about how we represent the world in the first place. Our brains don't process information in a static, frame-by-frame way. It's always dynamic, always changing. And our understanding of the world is intimately tied to our interactions with it, our embodied experience. The way deep learning treats space and time as just another dimension of the input, it's too simplistic. The relationships and correlations within those dimensions are really what matters, and we might need something that can dynamically switch between different representations to really grasp these relationships. I mean, take spatial awareness, or the way we imagine ourselves moving through space. That's not something that's easily encoded in the kind of matrix transformations we see in deep learning. We don't just compute locations, we infer relationships to other objects and use that understanding in action.
Right. And that's where I think neuroscience has a lot to offer. Our brains are incredibly efficient and don't just brute force these things. I mean, look at how the hippocampus is able to use the grid cells to encode space and create a cognitive map. It's like the basis of our spatial understanding. And we can use that as a basis to encode spatiotemporal relationships. It's not just about learning from huge data sets, but about how information is organized and represented within the system. And I think that we should combine these ideas from neuroscience and AI so that we can get a better understanding and build more intelligent machines. We need a better grasp on how the brain builds these internal models and how those maps are related to the real world through action and perception. It's a more holistic picture than just raw statistics.
Okay, I get that. The brain's architecture is fascinating. But let's not underestimate how rapidly deep learning is evolving. The new architectures are so incredibly powerful, and while current models might struggle with true causal reasoning, I've seen research where you can augment these models with symbolic layers that can perform reasoning and logic. We're adding that capability. We're also seeing how these models are able to learn things from relatively small data sets. It's all about the training procedures and model architecture, not just the data. And don't forget, the sheer scale of data available is constantly increasing. Think of the internet as a massive training data set. We're still at the beginning of exploring the limits of what's possible with deep learning. It's like we've just discovered a new kind of energy, and now we're figuring out how to harness it. I also think that we should not assume that the brain is the pinnacle. It was shaped by evolution, but it doesn't mean that it's the optimal way of creating intelligence. We might go beyond it.
But that's the problem. We're just throwing data and hoping something intelligent emerges, rather than building a system that has a built-in mechanism for understanding. We need to focus on neuro-symbolic approaches that use rules and logic. Look at how humans learn. It's not just by memorizing data. It's through abstract rules and logical deduction. For example, if you see something falling down, you understand gravity as a fundamental principle, and you can apply it to other objects falling down, not just that specific object. Deep learning systems need to be able to do that, to learn these higher-level concepts. I mean, look at the field of knowledge graphs. They're attempting to represent knowledge in a structured way. If you combine that with the learning capabilities of neural networks, then I think we might have a better path towards AI.
And I agree with the need for explicit structure, but I also think that the symbolic representations need to be able to dynamically shift as they move through space and time. They can't be static. It can't be a static graph. It needs to be something dynamic and interactive. I mean, consider how our perception changes as we move around an object. We're not just receiving a series of static images, our brain's constantly reconstructing and updating a 3D model. Our representation of the object is constantly being reformed and transformed as we move. We need something that can take these different coordinate systems and perspectives into account, and we also need that understanding of embodiment. We need to move beyond the static snapshot view and move towards a more dynamic understanding of space and time. This requires something beyond deep learning. I think what we are missing is an algorithm that can translate different coordinate systems with an embedded understanding of the spatial and temporal context.
Yes. And I think that this is where we can really draw some inspiration from the brain, We see that the brain uses various coordinate systems to represent space, like egocentric and allocentric, and there's this dynamic transformation happening between them. The idea of combining these perspectives is crucial. It's not just about having one correct coordinate frame, but about how these different perspectives relate to each other. For example, the dorsal and ventral streams are constantly interacting, one processing location and movement while the other processes the identity of objects. The key is in the transformation between them. So, I really do think that we need a more hybrid approach, combining the learning capabilities of neural networks with the structuring principles and transformations inspired by neuroscience.
But what about how good deep learning has become in handling different coordinate systems? It does a pretty good job of translating images, for example, from a front-facing camera to a side one. I think that you're underestimating the capacity of these systems to learn complex coordinate transformations. These models are doing really well with computer vision and understanding spatial layout of a scene. I mean, think of the ability of self-driving cars to navigate in a complex, dynamic environment. That's not just brute force pattern matching. They're understanding spatial relationships, object tracking, and, to a certain extent, are creating 3D models of their surroundings. And these things are not explicitly encoded. The models are learning them from data. I'm also intrigued by these new ways of training where you introduce a form of meta-learning, where the model learns how to learn. So you are not manually encoding them. I still think we're closer than you guys think to AGI through scaling deep learning.
But those systems have huge flaws. They fail on basic edge cases. The training is very specific and they aren't flexible. They lack the flexibility and generalization that humans have. And to me, this speaks to the underlying issue of them lacking a real understanding of the world. And these computer vision systems, they are incredibly fragile and can easily be fooled with adversarial examples that are totally invisible to the human eye. The kind of symbolic reasoning and abstract rules that we are using, that's what gives humans the ability to adapt to novel situations. And that's what's missing in current deep learning systems. I am not saying that deep learning should be ignored, but that it needs to be integrated with other methods. We need to bridge these gaps with reasoning and logic.
And it's not just that it's fragile, it's that it requires an incredible amount of data. The way that humans learn and generalize is vastly different from how these systems work. And you're right, the edge cases show the limitations of how this representation of space is done. It's not that these systems can't translate. It's that their representation is purely learned from correlations. It is not embedded into the architecture. It's not encoded in such a way that can then generalize to radically different perspectives. They have these blind spots. What we need is an architecture that can dynamically switch between different coordinate systems, a system that can learn how to learn, that can construct its own internal models of the world and translate between them. What would happen if we give the model an algorithm that allows it to switch between egocentric and allocentric coordinates? That's my point. It's not about just throwing more data at it, it's about understanding the fundamental algorithms that govern cognition.
Right. I think you are onto something there. And there's a lot of evidence from neuroscience that points to the importance of dynamic transformations. The brain is not a static structure. It's constantly adapting and changing its representations based on the task at hand. And there's this interesting research where they are training neural networks to emulate the properties of grid cells, and the results are fascinating. When these networks learn to represent space with these kind of representations, they can perform complex path planning and navigation tasks with a remarkable efficiency, and it all emerges as a consequence of the architecture, and it all emerges as a consequence of the architecture and the way it encodes space. I think that these kind of findings are a clear indication that we can benefit a lot from looking at the neuroscience of navigation. It is a blueprint of how a system can use space in a very effective way, and we should use it to build more powerful AI.
But that still seems like trying to directly copy the brain, which might not be the most efficient route to artificial intelligence. I mean, birds fly, but we didn't create planes by flapping our arms. The principles are there, but the execution might be different. With large language models, we're seeing that the scale of the model is enough to unlock new levels of ability. The same way the sheer size of the bird's wing is what lets it fly. I think we should pursue both tracks, sure, learn from neuroscience, but don't get stuck there. The advances are happening so quickly with deep learning, we have to see how far it can go. Maybe we should think of the brain not as the only way of getting intelligence, but just one solution to the problem. There might be alternative paths to AGI that we haven't even conceived of yet. But I am saying, deep learning has potential that we haven't fully tapped into.
I think that you are missing the point. It's not about copying the brain directly. It's about understanding its underlying principles. These neural networks may be good at pattern matching, but they're really struggling with abstract reasoning. The human ability to solve logical problems using symbolic representation and to understand abstract concepts like causality is not just about processing data, it's a whole different approach, one that is not captured by large language models. I do think that there is something there, and that we should focus on developing neuro-symbolic systems, combining the pattern recognition ability of neural networks with the symbolic manipulation of logic-based systems. And that's not just a theoretical approach. There are some promising results in the research that show that we can make these kind of hybrid systems.
Exactly, it's about extracting the principles, not necessarily copying the brain exactly. And the spatiotemporal representation, that's a fundamental part of how we interact with the world. It's not just about where something is, but also its motion and the way it changes over time. The way that our brains can create an internal model of the world and understand spatial relationships. It's all tied to our sensory motor feedback loops. It's about the constant interaction of perception and action. I am advocating that we need a system where the representation is not just static, but dynamic and adaptive, something that can understand the relationships between different coordinate systems and use them to infer spatial and temporal information. I think that we're fundamentally missing an algorithm that can do this in a general and efficient way. Deep learning might be a good tool, but it doesn't give us this core algorithm.
And I'm completely on board with that. I think that this idea of a dynamic and adaptive representation that is able to transform between different coordinate systems is really crucial. It's not about copying the brain. It's about understanding its mechanisms and principles. We need to be looking into how the brain transforms information and how those transformations are related to learning and understanding. I think that we have a lot to learn from the neuroscience of perception and action, of how the brain uses feedback loops to build and adapt its internal model of the world. This is where we need to focus. We need to combine those findings with the power of AI to build systems that are truly intelligent, systems that can not only generate patterns but understand the world in a more fundamental way.
Okay, I hear what you're all saying. I do see the limitations of current deep learning models, especially when it comes to causal reasoning and the dynamic representations. But I still think that we should push the boundaries of deep learning further. I think we should be exploring the limits of what's possible with large language models and multimodal systems. Maybe we need bigger data sets, novel training methods, or even model architectures. Maybe the key is in creating systems that can actively explore and learn from the environment, not just from passively ingested data. And I think we might see new algorithms emerge through the deep learning community, especially with the kind of meta-learning approaches that are coming up. I'm not saying that we shouldn't learn from neuroscience, but that we shouldn't limit ourselves either.
But that's just more of the same approach, brute force, and hoping to find a general intelligent system. We need to focus on the fundamentals, the abstract principles that enable intelligence and not just training systems on massive data sets. I think we need to invest more in research into neuro-symbolic approaches because this combines the strengths of both methods, the pattern recognition abilities of neural networks and the logical reasoning power of symbolic systems. And this means that we will be able to create AI systems that can perform more complex reasoning, problem solving, and learning, and also be able to better generalize and adapt to novel situations. We also need to address the brittleness of deep learning models and create systems that can be more robust, flexible, and trustworthy. We should build a solid foundation that combines both approaches and not just rely on one of them.
And I think the key is in how we represent space and time. We are fundamentally missing something there. We need to create an algorithm that can perform dynamic coordinate transformations that can translate between different frames of reference, that can take into account the spatial and temporal relationships of objects in the world. We need a system that can go beyond the static snapshot view and construct dynamic, adaptive representations, and that understands that the same object is seen differently from different viewpoints. We need to encode these transformations in the architecture to really grasp how humans navigate, learn, and understand the world, because I really believe that is where the core of cognition comes from. Current deep learning models are very much brute force. We should really be looking into those core algorithms that might lead us closer to AGI.
Right? And I think we're all agreeing on the importance of a more integrated approach, even though we might have different opinions on how to get there. I think that the future of AI relies on combining the strengths of different approaches, not just relying on one single method. We should be exploring both, expanding the capacity of deep learning, but also delving deep into the fundamental principles of neuroscience and cognition. We need to integrate those findings into AI systems to create something that can not only match human performance, but understand the world in the same way we do. And from my perspective, we need to double down on neuroscience and explore the algorithms it uses to efficiently represent space and time. The way the brain does it is incredibly effective, and it has a lot to offer us when building better AI.
Okay, so taking a step back, it's clear there are multiple paths to AGI, and we shouldn't dismiss deep learning yet. I think the way forward is to keep pushing the limits of deep learning models, exploring new architectures, training methods, and data sources. We should also explore meta-learning techniques that allow the models to learn how to learn and create systems that are not just passive learners, but also active explorers. And while we do this, we should also look into incorporating symbolic reasoning and logic into those models. My research will be focusing on how we can extend deep learning further and how we can address its known limitations with novel architectures. I think we still haven't fully unlocked the potential of neural networks, and the next few years are going to be very exciting. The scaling laws might lead to something beyond our current understanding.
And my focus is going to be on neuro-symbolic approaches. I really think that is the key to unlocking more advanced capabilities like reasoning, abstraction, and generalization, which is what we want in AI. I want to investigate how we can combine the pattern recognition of neural networks with the symbolic manipulation of logic-based systems to create something powerful. I also want to address the brittleness of deep learning models and create more robust and flexible systems. My research will be focusing on how we can bridge those gaps and how we can create systems that can both reason and learn from data. And I really think that is where the future of AGI is, not just blindly throwing data at models.
And my research will revolve around the spatiotemporal representations. I think we are fundamentally missing something on how we represent space and time, and we need to be looking at how the brain achieves that includes the way it transforms different coordinate systems. I'm focused on finding an algorithm that can dynamically switch between different frames of reference and how this links to action. I will investigate how we can encode the transformations in the architecture, not just the learning. We need to move beyond a static snapshot view of the world and create adaptive dynamic models, and that is where I think the key to AGI really lies, in this deep understanding of the spatiotemporal dynamics of perception and action. I really want to find the core algorithm that underlies this process.
Absolutely, and I think that's a great note to end on. It's always so fascinating to explore the different viewpoints, and it highlights how much there is still to discover. Thanks everyone for joining us today. And remember, the journey towards understanding intelligence, whether it's biological or artificial, is a continuous process, a spiral that keeps evolving. We need to keep pushing boundaries and exploring different approaches. And we will definitely be revisiting these ideas again soon. So stay tuned for our next episode.